This is going to be about using U-substitution to integrate composite functions. Before we integrate, let's look at what happens when we take the derivative of a composite function. So the derivative of f of g of t. I start on the outside and take the derivative f prime of g of t, and then I work my way in, g prime of t. If I have an example with y equals cosine of x cubed, the derivative of y with respect to x, again I start on the outside, the derivative of the cosine is negative sine of x cubed times the derivative of x cubed, which is 3x squared. And I just write that out in front. The 3x squared is the inside or the composite part of the function. So if we want to think about undoing the chain rule, we're not going to undo a product rule, but we're going to look at the du part of the function. So if this was my problem, the integral of 3x squared times the sine of x cubed, you kind of know what the answer is. But how I'm going to think about that, this is my big function, sine, this is my u. If u is x cubed, then du is 3x squared dx. Oh, I have that exactly here. So I'm going to just rewrite this as the integral of sine of u du. If I did not have at least an x squared here, I couldn't do this problem because I can't divide by another function. That creates a quotient rule kind of problem. So, the antiderivative of sine is negative cosine of u du. Then I'm going to go back and put my u in. So because we're started off with respect to x. So my antiderivative, whoops, I'm sorry, there should not be a du here. Negative cosine u plus c. So my antiderivative is negative cosine of x cubed plus c. If I want to look at an example with the power rule, I've got x times the quantity 5x squared plus 9 to the third. The whole function to the third power is my big function, my outer function. My inner function is the 5x squared plus 9. So I'm going to let this be my u. U is 5x squared plus 9. That's going to make this u to the third when I come back to integrate. The derivative, du, is 10x dx. When I substitute, I have to substitute exactly. I see I have an x and a dx. I do not have a 10, but I can divide by 10. I can always multiply or divide by a constant. So I can say 1/10 du equals x dx. And I'm going to make this substitution exactly into my original problem. 1/10 du, I've already substituted the u. Now this becomes a pretty easy problem, because the antiderivative of something to the third is something to the fourth over 4. So this becomes 1/10, which stays there, u to the fourth over 4 plus c. And now I'm going to go back and put my u in, because we started off with respect to x. So my final answer is going to be 5x squared plus 9 to the fourth over 40 plus c. This is a similar problem. My something to the fourth. My u is going to come from the inside function. So u is going to be 5x cubed minus 1. Du is 15x squared dx. I don't have a 15, I have a 3, but I'm I'll worry about that. What I'd like to do is just substitute for the x squared. So I'm going to divide by 15. So my 1/15 du is going to be x squared dx. So I'm substituting for the x squared dx. That's 1/15 du. I still have my 3 here from the original problem. And I'm going to substitute for this 5x cubed minus 1. That was my u. I write everything out and then I can go back and check. So that becomes u to the 4th. Now, I'm going to go ahead and simplify the 3 and the 15. Now I'm ready to integrate. So I've got 1/5. The antiderivative of u to the 4th is u to the 5th over 5 plus c. And I can multiply the 5 and the 5, and I'm going to go and substitute back in for my u. So my final answer is 5x cubed minus 1 to the 5th over 25 plus c. Anytime I've got a composition of functions, I'm going to do a U-substitution because we're not undoing the product rule. This extra x or x squared out in front is to help us accommodate the U-substitution or the chain rule.